I hope you are following my lectures, and if not, you please send an email to this address, and then I can clarify any of your doubts. And my suggestion is you please complete reviewing all the previous lectures before you listen to the next lecture, so that you can follow the sequence, because in this course every lecture is based on what you have learnt in the previous lecture. So my suggestion is please be up to date and work out all the tutorial problems and then listen to the lectures before you move on. Okay, so let's continue. In the previous class we had discussed about the different nonlinear analysis techniques, and let me just review once again and then show you an Excel spreadsheet program for doing this analysis. So it is, I am going to review whatever we had done in the previous class and then show you one Excel spreadsheet for you to do the calculations, and that will help you in quickly learning these concepts. So depending on the problem that we have, we can analyze differently, and the simplest system that we can analyze is the linear elastic system, where our stress and strain are just linearly proportional to each other both during loading and unloading. And in that case we can just write our equilibrium equations as just simply K times U is equal to P, where K is our stiffness matrix, U is the vector of displacements, and P is the vector of applied forces. And in all the finite element analysis, you can either apply a force at a degree of freedom or a displacement. You can apply only one of them, and although I am saying we apply the force, we might as well apply the displacement, because as we have seen earlier with the example of the two blocks attached through an inclined joint element, where we applied equal vertical displacements at the top and then measured the reaction forces. So in this case, in the linear elastic systems, we don't really need to check for equilibrium. It's automatically satisfied, because whatever is the developed stress in the elements, they will be able to support that much stress, because there is no limit on the stresses that you can apply. And normally we don't write the right hand side in an incremental form, either as a dP or P minus reaction force, as we do for other systems. Then slightly more complicated are these nonlinear elastic systems, and the simplest one is just go in an incremental form, apply the force or displacement in small increments, so that you can follow this stress strain path as closely as possible. And our K is now the tangent stiffness matrix, because with increasing stress or with increasing strain, your slope is changing. So we update our constitutive matrix and then update our stiffness matrix, multiplied by incremental displacement is equal to incremental load corresponding to some incremental stress. And then as we are doing, we have to go on accumulating the displacements, strains, stresses, and so on. So our Pi is Pi minus 1 plus dPi, where I minus 1 corresponds to the previous step and I corresponds to the current step. And so the displacement, once you calculate the incremental displacements, we can update our displacement vector, and then you can calculate your strains as B times du, and then update our strains as the epsilon I is epsilon I minus 1 plus d epsilon, and then we can calculate the stress increment as d times d epsilon, and then update our stress vector sigma I is sigma I minus 1 plus d sigma I, and all these we are going to do at each and every integration point. Within the element we will have number of integration points depending on the order of element and so on. Okay. And in all these problems our stiffness matrix needs to be updated every iteration. Then once we update, we have to assemble, and then we have to triangulate, like we have to make it as an upper triangular matrix and so on. So these analysis, they take a lot of time, and actually this is one simple method, but we can actually improvise this, and that is shown here. And this equation that you are seeing, this equilibrium equation, it is valid for all types of nonlinear analysis problems, or inelastic, elastic plastic, or construction and execution problems. Whatever may be, this equation can take care. Once again, our tangent stiffness matrix multiplied by dui is P external minus B transpose sigma I minus 1. Actually this is the current applied force, and B transpose sigma I minus 1 is the reaction force from the previous iteration or previous step, and this sigma could be corrected stress, because when we have any limit on the stresses that we can apply, then we correct, and then the sigma could be a corrected stress. In that case our equilibrium gets disturbed, and this particular form of the equilibrium equation, it's the most important one in all our nonlinear finite element analysis, and you have to understand this perfectly, and once you understand, then you appreciate how we can apply this for all types of problems, like especially when we have the execution type problems, we need this for calculating our traction forces to make the excavated surfaces as free of traction. And then when we are iterating, we have to monitor the incremental displacements and then the outer balance force, and dpi is the outer balance force, or the difference between the applied force and the reaction force, and in the ideal case this should be 0, and that is what we get in the case of linear elastic problems. And in the other cases we satisfy this only in an approximate sense, as like we calculate some norm of outer balance force as a sigma of dpi square, the sum total of all the squares of the outer balance forces at all the degrees of freedom, and divided by square of all the applied loads multiplied by 100%, and we iterate until this value is less than about 0.1 or 0.5%, or sometimes even 1%, depending on the type of nonlinearity. If it is a highly nonlinear system, or the strength is limited, then we may tolerate slightly higher errors like 1%, 2%, so that we can complete the analysis quicker. And what if we do not apply any force? See, the right hand side pi is 0 when you do not apply, say if you have a displacement control analysis, in that case we just take it as some value 1, so that your denominator is not 0. Then the other norm that we monitor is the norm of incremental displacements. This is the square of incremental displacements, the sum total divided by the sum total of the squares of all the displacements, and once again this should be about 0.1 to 0.5%. Then there is another force norm, that is the incremental work done, that is the dp multiplied by du. We can monitor that also, and I will show you that quantity later when we deal with finite element analysis. And there are different solution methods that we can adapt for different problems. The simplest one is the initial stress method, then the tangent stiffness, and then a mixed method, combination of initial stress and tangent stiffness, and then secant stiffness method. And there is another method called as the initial strain method that is more applicable for viscoplastic or viscoelastic type problems, and I am not going to discuss this method in this course. In the initial stress method, our stiffness is kept constant, and then we apply some stress, and then at each stage we see what is the out of balance force, or what is the difference between the stress applied and then the actual stress that the material can support corresponding to that particular strain level. And then we apply this back on the system, and then get your incremental displacements, incremental strains, and other things, and then we repeat this process until your out of balance force is negligible. In the process, we are not going to change the stiffness matrix, it remains constant. That is why it is called as the initial stiffness or initial stress method. And the slopes are all constant, and it goes very fast because we are not going to reformulate our stiffness matrix. We formulate only once, then subsequently we do only the back substitution for determining the displacement increments. And yesterday I have shown you one small example of this nonlinear equation. Sigma is 600 epsilon minus 1200 epsilon square, and in this case our tangent modulus Et is d sigma by d epsilon, and this is actually it's a one dimensional problem just for hand calculation, so that we can illustrate the procedures more easily. The tangent modulus is d sigma by d epsilon, that is 600 minus 2400 epsilon, and the initial modulus is 600, that is when epsilon is 0. And then let us say that we are interested in finding what is the strain corresponding to an applied stress of 65, and by solving this quadratic equation we get two values for strain, that is 0.1587 before the peak, that is during the strain hardening part, then beyond the peak 0.33. But in this course we are going to deal with only the strain hardening part before the peak, and beyond the peak also, like that is corresponding to the strain softening part, and that will come later. And this is the procedure for initial stress method. This is the step by step method. So our applied stress is 65, and our initial modulus is 600, that is going to remain constant. So we apply this 65. Our initial guess on the strain is 0.1083, and the corresponding stress at strain of 0.1083 is 50.803, and then the difference between the applied stress and then the stress corresponding to this strain of 0.1083 is 14. We apply this back on the system and then get an incremental strain and our total strain, and then our stress corresponding to this strain, and then we calculate once again the out of balance force, and then repeat the process until we are happy with the solution that we get. Like we compare our out of balance force to the applied stress, and then within about 1% or 0.1% we can go on iterating, and then once you are happy with the out of balance force that you have, you can stop the and in this case within about 6 iterations our total strain obtained is 0.1573, which is very close to this value of 0.1587. Well, actually it is a very simple problem, and also the nonlinearity is not very high at 65. When we go to the Excel spreadsheet, I will illustrate this a bit more, and this is the result from our spreadsheet program. I will explain it when we go to the spreadsheet. And then the other one is the tangent stiffness method, where at every stage we calculate the tangent stiffness and estimate our new strain increments. So, the first time we are going to apply with initial modulus of 600 for this particular case, then we get this outer balance force, and then calculate our strain increment in term by as the ratio between the outer balance stress divided by the tangent modulus at this strain level, and then we repeat this, and as we proceed your tangent modulus is going to reduce and your strain increment is going to be very large compared to what we had earlier. Then we can reach the convergence very fast in this tangent stiffness method, because we are following the curve as much as possible. So, that is what see within 4 steps for the same problem our outer balance stress is nearly 0, whereas with the initial stress method even after 6 iterations there was some outer balance stress, and our total strain calculated one is 0.1587, which is exactly equal to the solution of that equation. And the problem with the tangent stiffness method is the slope will go on reducing as you are nearing the peak, and at the peak your slope will be 0, and then your modulus becomes negligible, and then you might start having numerical issues, and especially when you go into the strain softening part your modulus becomes negative, and if too many elements have a negative modulus, then you cannot work with that stiffness matrix, and you will get numerical problems, or the program will just simply stop saying that one of the diagonal elements is negative. In that case we can go in for the secant stiffness method, where the secant stiffness is the stress divided by the corresponding strain, and in this case our secant stiffness will always be positive, and it goes on reducing, because as your strain is increasing, stress will reach some peak value, and the rate of increase of stress may be lower compared to the rate of increase of the strain, and as you are reaching the peak your secant modulus will reduce, and especially in the strain softening part your stress is decreasing while your strain is increasing. So, in that case our tangent modulus or the secant modulus will fall rapidly, and in a way the secant modulus method is more stable for strain softening type problems, and in this case the secant stiffness is sigma by epsilon, and that is 600 minus 1200 epsilon, and then these are the results with secant stiffness method. After 6 iterations our total strain is still 0.1579, whereas even with the initial stress method we got about 0.1583, and our outer balance stress was slightly smaller in that case. These are the results from the Excel spreadsheet program, and now let me illustrate this with the, you will find this Excel spreadsheet program in your course material, and it is called as initial tangent and secant stiffness, and this particular equation that we are solving is A epsilon minus B epsilon square, and A is 600, B is 1200, the way we have it seen, and the maximum stress that you can apply for these properties is 75, and that depends on this A and B values. Like, let's say if your B is 1400, your maximum stress that you can apply is 64, okay, and so I am setting it back to 600 and 1200, and then the maximum stress that you can apply is 75, and the strains in the hardening part is 0.1587, and the strain during the softening part is 0.34, and we are interested in determining the strain corresponding to an applied stress of 65, and for now we will only be looking at the strain hardening part. We are not going to go into the strain softening part. So our initially our applied stress is 65, and so we can call that as the outer balance force, and the strain increment is 65 divided by B4. I hope you know the Excel spreadsheet programming. If you indicate anything with a dollar sign, that will refer to one particular cell or one particular column. $B, $4 means column B, and row 4. So that is fixed. And then if I say D11, it is initially it is D11, and then next one it will be D12, and so on. Okay. So here this 0.1083 is the outer balance stress in the previous step divided by 600. So that B4 is our 600, and then our total strain at this stage is 0.1083, and our outer balance stress is the applied stress of 65 minus the reaction that we get from our stress equation A epsilon minus B epsilon square, and then we take this new outer balance stress of 14, that divided by 600 is your strain increment. This is our total strain, and then now the outer balance stress is 65 minus the stress corresponding to the strain of 0.1318. Okay. And then we calculate the new strain increment, and then the total strain, and then outer balance stress, and so on. Like, we go on continuing until we are happy with the solution that we get. So here I think in the class example we stopped here, and that is after 1, 2, 3, 4, 5, 6 iterations, our outer balance stress is 0.809, and the total strain is 0.155. Okay. And we can continue for as long as we want. Okay. And it's a very simple procedure, and let's apply. Actually, let me show you the stress strain curve. See here, this is the stress strain curve that we have, and we are trying to solve for the strain at a stress of 65, and then if our applied stress is very close to the peak, then we need more number of iterations, because you see here there is lot of non-linearity, and if it is only 20, we are still within the maybe very close to the linear limit. So we may not need many iterations. So, let me just do this. Say if I apply a stress of 20, it's our strain is 0.0359, and within 4 steps we get that strain even with the initial stiffness method, because the stress is very small and we are within the elastic limit. And let us see, I increase this to 74, very close to the ultimate stress. In this case, we will our strain is 0.221, and we see here we need a very large number of iterations, like after about maybe 30 iterations we get about 0.22, and the outer balance stress is 0.064. Okay. And if you apply a stress of 75, then we will have a problem. In fact, the program will get confused, because this is the peak point. So, there is no difference between strain hardening and strain softening, and the program gives the same stress value, because it cannot distinguish, because that is the peak point, 0.25. And if you see here, it is going on and on and on, and 0.25 we are not able to reach. We are reaching that after almost maybe more than 200 oops, it's actually even after 400 cycles our total strain is 0.2488. Okay. So, depending on the problem that we have, your number of iterations might change. Okay. Let me just set it back to 65. Okay. And within 6 cycles our total strain with the initial stiffness method or initial stress method is 0.155 against the calculated strain of 0.1587. Okay. And now let us look at the tangent stiffness method, where we update our stiffness matrix or our stiffness. We are doing the same thing. In the first iteration, our outer balance stress is 14, and then we calculate the stiffness at this strain of 0.108, and if you see here, the tangent stiffness is A minus 2b epsilon. Okay. That is so the tangent stiffness becomes 340, and our incremental strain is the outer balance stress divided by 340 instead of 600. So, our total strain has increased to 0.149, and then our outer balance stress has reduced, and our tangent stiffness has reduced, and within about 5 cycles, 1, 2, 3, 4, 5 cycles, our incremental strain is negligible, and our outer balance force is also negligible. And whereas after 5 cycles, 1, 2, 3, 4, 5 cycles, the total strain with the initial stress method was 0.1529, whereas here we are able to get our value, exact value of 0.1587. And let me increase this stress to 74. Okay. And our strain is 0.221, and even with the tangent stiffness method, within about 5 or 6 steps we are able to get to that strain level, whereas with the initial stress method it is taking a very long large number of iterations. 2 to 1 we are able to get at about after about 50 cycles. Okay. and let me just get back to 65, and let us see what happens with the secant stiffness method. Actually, the illustration is also shown here, and with the secant stiffness method, our secant stiffness is sigma by epsilon, that is A minus B epsilon, and our initial outer balance stress is 65. 65 divided by our initial modulus of 600 is 0.108, and our outer balance stress is 14, and our secant stiffness at this strain level of 0.1083 is this A minus B epsilon, that's 470, and this is our incremental strain and our total strain, and then the outer balance stress, that is the applied stress of 65 minus the reaction stress, and then the secant stiffness. So, you see here, as the strain is increasing, your secant stiffness is reducing, and the same thing with the tangent stiffness. Okay, and so we are actually, what is our exact result is 0.1587, and in this case, after about maybe 20 iterations, we are able to get that exact value where our outer balance force is negligible. Okay, and this method is quite easy to implement, the secant stiffness, and because our stiffness values are always positive definite, we will not have any problem. Okay, let me just apply a stress of 75 and see what happens. Okay, that is and our strain corresponding to a stress of 75 is 0.25, and our tangent stiffness method is able to predict the stress after a large number of iterations. But then this being a small problem, it's not an issue, because your tangent stiffness is very low, 0.009. But if it were a large finite element program, these small values will compound with each other, and you might start forming a mechanism with very large displacements. But this being a small problem, we are able to converge without any numerical issues. So, here after about 20 cycles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 iterations, we are able to get to the exact value with the tangent stiffness method. And with the secant stiffness, we see that even after about 35 cycles, it has not reached the 0.25, and with the initial stiffness also, it takes a very large number of iterations to get that 0.25. In fact, that we have seen earlier, we did not reach. Okay, so depending on the situation, in some problems we might use initial stress method, and tangent stiffness we should be very careful, because in most cases the solutions will simply diverge, because our denominator becomes smaller and smaller with each load increment, and then at some point the denominator might become so small that your displacements could be very large. And both secant stiffness and initial stress methods are very stable, and the initial stress method is very fast, because we are not reformulating the stiffness matrix, and the tangent stiffness method is very slow, because at each and every step we are updating our stiffness matrix, and we can combine the initial stiffness and tangent stiffness, and maybe we can update our stiffness matrix every say 10th iteration or something like that, and in between we can use the initial stiffness method, so that we can economize on the number of computations. Okay. So, this is a brief introduction to the different analysis methods. Just to summarize, let me show you with this example, with this figure. We have the initial stress method where our stiffness matrix remains constant, and then the tangent stiffness method where we follow the stress strain curve as closely as possible by taking a tangent modulus as d sigma by d epsilon. Then the other one is the secant stiffness, where our modulus is stress divided by strain, and that is also very stable because our stiffness values are always positive definite, and we can get reasonably good solutions. But then the secant stiffness method also takes up a lot of time because every time we have to update our stiffness matrix and do the calculations. Okay. So, that is the brief introduction to different nonlinear analysis methods, and we will see more of this later on when we are doing the finite element analysis. So, thank you very much. We will meet in the next class.